Hello and welcome. I am Sumit Chaube and this is going to be a lecture on finite field for error control coding, or you can say that it is going to be a series of lecture on finite field for error control coding. Engineering is basically applied mathematics in disguise, and modern algebra serves as the basic foundation for error control coding. So we are going to discuss some basic algebraic structure, and these lectures are going to be fairly simple, fairly basic in their contents, and you can say it's going to be very elementary. Finite field or Galois field, actually it is called Galois field, sorry for my pronunciation. In mathematics, finite field or Galois field, it is called Galois field in the name of Évariste Galois, who was a 17th century mathematician, quite a genius person actually, is a field that contains finite number of elements, and as with any other field, it's going to have certain operations like multiplication, division, addition and subtraction. Now, since division is basically multiplication in disguise, or subtraction is basically addition in disguise, you can say that there are only two elementary operations, and these two operations actually satisfy certain rules. So we are actually here to discuss these rules, okay? But before we actually learn about finite field, we have to learn about certain basic algebraic structure, namely group and field, and then after that we can proceed to Galois field or Galois field. So we will start with the group. Group is basically a doublet. What I mean by that is that it's a group is underlying set and a operation star. So that's why it is called doublet. We have a set G and star. So sometimes I'm going to use G just for group, and sometimes I will call it underlying set. Anyway, it's mean the same. So we have an underlying set together with an operation, and this operation star is binary in nature. Okay, so this is going to be called a group. This doublet is going to be called a group if it is going to satisfy certain axioms. And the very first axiom that it has to satisfy is closure. What I mean by closure is that if A and B are element of G, then A star B should also be an element of G. So this is what it means by closure. That the result of this operation, if the two elements A and B are in G, is also going to be in G. Second is associative law, which what it means basically is that for all ABC element of G, A star B star C is actually equal to A star B star C. So order of the operation doesn't really matter. That's what it means by associative law. Now the third one, we have identity. G contains an element E, an identity element of G, such that for any A element of G, A star E is equal to E star A, and that is equal to A. So identity element doesn't change the element, doesn't change the element. Okay. Now the fourth axiom is inverse. For any element A in G, there exists another element A dash in G called inverse of A, such that A star A inverse is equal to identity element E. So this is the definition of your inverse. And additive inverse, if this operation star is addition, then A dash is called additive inverse. If this star is multiplication, then it is called multiplicative inverse, and we will see about them in a few minutes. Now, a group doesn't need to satisfy commutative law, but if it is satisfying commutative law, then the group is called abelian or commutative group. So abelian group is a group in which if you change the order, if you change A and B, if you change their places, it doesn't make any difference. Okay, so they are kind of symmetric. Okay, now one more definition with respect to group is order of the group. So order of a group is basically the number of elements in the underlying set. Okay, and this order of the group is actually different from the order of an element. So if you have a multiplicative group, then the smallest positive integer n such that a to the power n is equal to 1, then n is called the order of the group element A. And if it is an additive element, what you can say group, then this must be satisfied that n times A addition, so we are adding A n times, this must be equal to 0. Then this n is called order of this group element A. Okay, and we will see these definition later in detail. Okay, so here we have a very well-known group. It is addition under it is actually integer under addition. So we have an integer, set of integer is called z, and the operation here is addition. So if you add any two integer, the result is also going to be integer, so it is closed under addition. Addition is actually associative, so associative law is going to be satisfied, and with respect to addition, the identity element in the integer is 0. So if you have an element x which is integer, then x plus 0 is x, so 0 here is our identity element, so identity is also going to satisfy. And then inverse exists for each and every element. For example, if the element is I, then its inverse is actually equal to, inverse of I is actually equal to minus I, and this is called additive inverse of I. Okay, so for 3, the inverse of 3 is minus 3. Inverse of 0 is 0 only, minus 0 is 0. So inverse of 1 is minus 1, inverse of 3 is minus 3, inverse of 5 is minus 5, so on and so forth. Now we are going to see another group or another set with an operation multiplication. So we have a set of non-zero integers. So this cross means here that we don't have 0 in integer, and we are considering this because for inverse you have to divide it by a certain element, and division by 0 is simply not permitted. You will see that in a very few minutes. Okay, so if you multiply two integers, you are going to get integers, so closure is satisfied, associative law is going to be there, identity element is there. 1 is actually multiplicative identity, so for A times 1 is actually equal to A, so 1 is your multiplicative identity here. Okay, and but inverse doesn't exist for an element. For A inverse will be simply 1 upon A, because A dash should be equal to 1, right? So 1 upon A may or may not be an integer. It may not be an integer. Okay, so for that's the reason we don't have n. This is not going to be satisfied. So this particular set under multiplication is not a group. Now next we are going to see rational number, non-zero rational number under multiplication. So we have closure, we have associative law, we have identity, and identity element here is 1, and inverse is also going to be there for A dash is equal to 1 upon A, and since it's a rational number, so if A dash is P by Q, then A is P by Q, then A dash will be Q by P. Okay, so this is going to be there. Next example of group is actually modulo 5 addition of integer. Now here integer, this notation, this notation here basically means z divided by 5z, is that when you divide any integer by 5, whatever the remainder is, that is going to be the set. So let me call this set G, and this set G is going to have 5 elements 0, 1, 2, 3 and 4, because these are the remainder that you can get when you divide any integer by 5. Okay, and we are actually doing modulo 5 addition. So if you have a plus this 5b, this is actually equal to a plus b divided 5 by 5. So remainder when a b is divided by 5. Okay, so to demonstrate all these what you can say properties, I have included a table here. So we have 0, 1, 2, 3, 4 here and 0, 1, 2, 3, 4 here, and this operation is modulo 5 addition. Now 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2. You can see here that 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, 2 plus 1 is 3, this 2 plus 3 is 5, but 5 under modulo 5. So let's say you have 2 plus 3 and you divide it by 5, the remainder is going to be 0. So that's why we have a 0 here. Okay, and additive identity here is again 0. So our additive identity is 0. You can see that in this Cayley table, this is called Cayley table in the honor of its the person who has used it first, Arthur Cayley. He was a British mathematician. He was the first one to use this table. So in this Cayley table, you can see that each column has all the elements of the columns are different, and that's the case with the row as well. Okay, and each and every column or row is going to contain your identity element, and here in this case our identity element is simply 0. Okay, and inverse does exist because you see that 0 is in every single row and column. Okay, so inverse exists for each and every element of this group. Okay, so it's going to be a group under modulo 5 addition. Then we have modulo 4. You can see that it's also, again we have included Cayley table here. So we have closure, we have associative law, identity and inverse. Next we have a what you can say non-zero element of the previous group. So we have we have 1, 2, 3 and 4. We have also included Cayley table here, and here multiplicative identity is 1. So modulo 5 multiplication is there. So what is modulo 5 multiplication? A plus 8 times, actually this is times 5, 8 times b is actually equal to a multiplied by b and then divided by 5, and whatever the remainder is there, that remainder r is the result. Okay, so again we have included our Cayley table here, and you can see that identity element is there in each and every row. So we have identity element each and every row. So identity element is there, or in other words you can say inverse exists for each and every element. So inverse is also there. It's going to be associative, and we are going to have closure. All these elements are only 1, 2, 3, 4. Okay, here we have another group, but here we are taking modulo 4 multiplication, and this is not going to be a group. In the Cayley table you can see that you are getting 0 here, and 0 is certainly not the element of this group. Our group is non-zero when divided by 4. So we have 1, 2 and 3, and 0 is not the element of this group. So we are getting 0. So this is not closed under modulo 4 multiplication. Associative law is going to be satisfied. Identity element is again 1. So identity element is 1. But closure is not there, and the similar manner inverse is not there. For 2 there is no inverse. Okay, you are not getting one identity element anywhere in this row. Okay, so this is not a group. So this is not a group. Next, we are going to see, this is a general result, that under modulo M addition, you are going to have a group. You are going to have a group under modulo M addition. It's going to satisfy all these property: closure, associative, identity, and inverse. But under modulo P multiplication, it's only going to be a group if P is a prime number. So if P is a prime number, then you are going to have a group. So as we have seen that modulo 5 multiplication, it was group. So if P, because 5 is a prime number, okay, so this is going to satisfy if P is a prime number. And you do remember, I hope that you do remember this. So these last two examples are actually a fact that we are going to use later in the detail. Okay, and you can prove it in general, but then video is going to be a much bigger, and I don't want it to be. Okay, so why these 4 axioms? So you can see that these axioms are there for us to, actually we are going to use any field for solving equation. So we are going to start with simplest equation there. So let's solve this equation. X plus 3 is equal to 5, and the group that we are considering is integer under addition. Okay, so to solve this, we have to add minus 3 into both left hand side and right hand side. And minus 3, why minus 3? Because minus 3 is inverse of 3, and so there must be inverse. Without inverse, you will not be able to solve this equation. And then we are going to solve this right hand side, 5 plus minus 3, and we are able to do this because this result we are sure that is going to be under our group. So this is closed under addition, and that's why we are able to do it. And then on the left hand side, we are going to change the order of these operations. And why we are able to do it? Because it is going to be associative. So association must be there. Okay. And then 3 plus minus 3 is equal to 0, and 0 is again our identity element. So identity. So these 4 rules must be there. Okay. For, to solve this equation. Okay. And the people who are in the business of making these axioms tends to be very laconic. They don't say until they have to say. So they just include finite number of, not so many. Okay, so now we are going to discuss subgroup, and it's actually fairly simple that a group H is said to be a subgroup of G if and only if H is a subset of G, H is not empty, and H is closed under the same group operation G and satisfies all the condition of the group. So if you have a group G, and G is like this, G under the star operation, then another group H under star AD, okay, is going to be a subgroup of G if and only if H is a subset of G and H is not empty. Okay, so one of the example is, for example, if the group G is like rational number under addition, then integer under addition will be subgroup of rational number under addition. Okay, so H, and this is less than equal to sign is it is like, we interpret it like this, that H is a subgroup of group of G. Okay, and there is a theorem with respect to subgroup that if H is a subgroup of G, then number of element in underlying set H must divide number of element in underlying set G. Now we are going to discuss 2 properties of the group. These are very important property, and the very first property is that identity element of a group G is unique. So let's assume that it's not unique. What I mean by that, let's assume that we have 2 identity element. One is E, another is E dash, and both of these are not equal. Means E dash is not equal to E dash, and actually I have written E double dash, but it's E dash anyway. So E is not equal to E dash. This is what we are assuming, and we are assuming that it is identity element. So if it is an identity element, then E can be written as E star E dash, because E dash is also identity, and if I operate it with some element, I will get that element only. So E can be written like this, and since E is also the identity element, this can be written as E dash. So you can see that E is equal to E dash, and which is a contradiction that we have assumed that E is not equal to E dash. Okay, so there must be, so our assumption must be wrong, right? So a group element is actually unique. So identity element is of the group is all actually unique. Now the second theorem is that inverse of an element in the group G is unique. So again we are going to say that, let's say that inverse of a group element is not unique. So let me take inverse of A as A dash, and it is not equal to A double dash, and A double dash, A dash and A double dash are both are inverse of this group element A. Then I can write E, identity element E, sorry, let me start with A. So A dash can be written as A dash with group operation E, and then E can be written as A dash, and I can write this E as A double dash, because A double dash is inverse of group. So when we operate these two, I will get A, and if I change the order, I will get A dash A and then A double dash, and you can see that this is going to be E, and then E operated with this is going to give me A double dash. So A dash is equal to A double dash, which is again a contradiction of this assumption that we have assumed here. So inverse of a group element is also going to be unique. Next we are going to consider a cyclic group. So a cyclic group is one in which all the group element can be generated using a single element, and that single element is generally called generator. So this single element is called generator, because using this we can generate all the element. Now we are going to consider a group G with these element 1, 2, 3, 4, and the operation that we are taking is modulo 5 multiplication. Then you see that 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8, and 8 mod 5 will be equal to 3, so we are getting 3. 2 to the power 4 is 16 mod 5, which is equal to 1. So we are able to get all the group element from this element only. So this element can be used to generate each and every element. So this kind of group is called cyclic group. Now homework here is that you have to prove that, you have to show that 3 and 4 are also generator for this group, generator of this group. Okay, so with the discussion of group, I hope that it is clear to you. With the discussion of this, I'm going to conclude this lecture, and I will see you in the next lecture when we will discuss a field. Okay, and after that we are going to discuss Galois field and properties and different things with respect to Galois field. Okay.